Multivariate adaptive regression splines, or MARS, is a non-parametric regression technique. It's fairly modern and was introduced in 1991 by Friedman. With MARS, you can model a continuous response variable by fitting a series of piecewise linear functions, which, in some cases, can be a significant improvement over using a single line. In this video, we'll demonstrate how to use MARS in R using the Earth and Caret packages.
Today, we're going to use multivariate adaptive regression splines on the Boston housing dataset. So first, we're going to start by loading any packages that we might need. So the Boston dataset is included in the MAS package. We're also going to load the tidyverse package to do some data visualization. We're going to load the Earth package, which has a function for Mars, which sounds a bit funny, but it's actually because Mars is trademarked. So rather than creating a function called Mars, the function is called Earth. And finally, we're going to load the Caret package, which is going to allow us to tune some of the parameters for our model. Next, we're going to set a seed to ensure that our results can be reproduced by someone else running this code. And as I mentioned, we're going to be using the Boston dataset. So first, I'm going to type $Boston into the RStudio console, and that's going to allow us to view the documentation for this dataset. So here we can see that this data set is in the MAS package. So there are a bunch of variables, but the response variable that we're going to be working with is a continuous variable, and that's equal to the median value of owner-occupied homes measured in thousands of dollars. Next, we're going to explore the data set a little bit just with some visualization very quickly. So specifically, we're going to be looking at this variable called LSTAT, which is the percentage of lower status in the population. So first I'm going to plot that using ggplot. So along the y-axis we have our response variable, which was that median value, and along the x-axis we had one of our independent variables, LSTAT. And we can see that the relationship between these two variables is certainly nonlinear, and we can verify that when we plot on a least squares regression line and we see that this line does not fit the data very well at all. Instead, if we had something that looked a little bit more like this, that might represent the data a bit better. So how can we figure out a way to do that? Well, multivariate adaptive regression splines is going to allow us to create a series of piecewise linear functions. So for example, we might be able to have one line here, and then another line here, and another line here, and so on. Now, of course, this is just one of the variables in the Boston dataset, so you can play around with this dataset and see what the relationships look like for the other variables. So before we create our model, we're going to create a train test split on our dataset. So we're going to have 80% of the observations in the dataset reserved for training our model, and then 20% of the observations reserved for testing the performance. For the training data, we're going to randomly sample 80% of the number of observations in the Boston dataset, and we're going to sample without replacement. And then we're going to create two subsetted data frames. So the first subsetted data frame we're going to call Boston_train, and that's going to be the Boston dataset at the training indices. So Boston_train is going to have 80% of the observations in our original dataset, and the Boston_test data frame is going to have the remaining observations. So that's going to be 20% of the size of the original Boston data frame. So next we're going to take a little peek at the documentation for the Earth function. So to do that, we can type $Earth into the RStudio console. And this is one of those functions that has very, very extensive documentation with many parameters that you can play around with. So we're not going to go through all of them, but we'll sort of focus on a few that you need in order to get things up and running. So the first thing that you're going to need to do is define the variables that you want to use for your response variable and which ones you want to use as your predictor variables. Now, if you're only doing this with one run of the function, you can use the formula and data arguments, which are very similar to any of the other modeling functions in R, such as LM or GLM.
But if you're planning on doing any parameter tuning, you might want to go with the arguments X and Y rather than formula and data.
Because we're actually going to be tuning a bunch of parameters, and the variables that we use as predictor variables might actually change on different runs of this function. So first we're going to specify x, which is going to be the independent variables, or the predictor variables, and then we'll need to specify y, which is the response variable. So then there's two other arguments that we'll play around with in this video. Degree is going to tell us the maximum degree of interaction, and by default that value is going to be set to 1, which means there are no interaction terms. So for example, if you want it to be possible for there to be some second order interaction terms, then you could set degree to 2. If you wanted it to be possible to have interaction terms up to a maximum degree of 4, then you could set degree equals 4. Next we have nprune, which gives the maximum number of terms, including the intercept, that can be included in the pruned model. So with this argument, you can place an upper bound on the model size, which could reduce the time required to run the function. So for example, if you had a data set and you wanted to make sure that your final model does not include more than 10 terms in the model, which would be 9 predictor variables and 1 intercept term, then you could set nprune to 10. So as an example, if you wanted to use this function, you could run it in the following form. So you would call the earth function, you would pass the argument x, which has your predictor variables. You would then pass the argument y, which has your response variable. And then you could pass on any other additional arguments that you want to specify. So for example, we could specify degree equals 2 and nprune equals 10. So that's if you wanted to run it just one time with only one value for each of these arguments. Let's say instead you wanted to play around with these arguments and try a bunch of different values for them. To do that, we're going to do something called a grid search, and we're going to use the caret package to perform that grid search. So before we jump ahead to that, let's start by defining our values for x and y. So if we look at the structure of the Boston dataset, we can see that our last variable is our response variable. And if we run the ncol function on the Boston dataset, we can see that the very last column is column number 14. So that tells us that our predictor variables are going to be all variables in the Boston dataset other than the 14th column. And our response variable is going to be just the 14th column. Next, we're going to create this parameter tuning grid that I was just mentioning. So basically what we're going to do is we're going to specify the values that we'd like to vary when we run the earth function on our training data. So just as an example, here I've varied the degree argument with the values 1 through 4, and I've varied the nprune argument from 5 to 50 in steps of 5. So let's run this and then take a look at what that looks like. So that has gone ahead and created a data frame for us where the first column contains the degree argument and the second column contains the nprune argument. And it's created every possible pairwise combination of these two arguments based on the arguments that we specified in that line of code. Here we've varied degree from 1 to 4, and we've varied nprune from 5 to 50 in steps of 5 each time. And then we've taken every possible pairwise combination to give us a total of 40 combinations of these two arguments. So in other words, we're going to run the earth function 40 separate times, and each time we're going to select one of these pairs for the arguments for degree and nprune. So now we're going to use the earth function, and we're also going to perform cross-validation when we train this model. So here we're going to use a function called train, which is from the caret package, and we're going to start by specifying the arguments that get passed to the earth function. So to do that, we're going to use the train function from the caret package. So I'm going to type $train into the console to take a look at the documentation for that function. So some of the arguments that we're going to need to pass are x and y, and those are going to be defined the same way as they were for the earth function. So we've already gone ahead and defined those, so that part shouldn't be a big deal. The next argument that we're going to need to specify is method, which is going to be a string argument, and we're going to need to specify which type of model we want to use. So specifically, we're going to pass the name of the function for the model that we're trying to create. So since we're going to be using the earth function, we pass method equals earth. Next, we're going to specify the metric used for determining what the optimal model will be. So there are a few different possibilities that you can use. Here, I've just chosen the default, which is RMSE, root mean square error, but there are some other options there as well. Next, we're going to specify the train control argument, which is going to allow us to specify any additional options that we might want while we're training this model. So here I'm going to use cross-validation by specifying method equals CV, and I'm going to use 10-fold cross-validation. So I specify number equals 10. And the last argument that we're going to specify is TuneGrid, which is the parameter grid data frame that we passed earlier. I'm going to run this now.
It should only take about 30 seconds to run.
Once that's finished running and we have all 40 of those trained models using the earth function, we can apply the ggplot function directly to that object that we just created in order to see the results that we obtained when tuning the parameters. So all I've done here is apply the ggplot function. I haven't changed any of the settings here. So this is the default plot that you would see when you use the ggplot function on an object of this class. So along the y-axis, we've got whatever we specified as our performance metric, which was root mean squared error. Along the x-axis, we've got the second parameter that we tuned, which was the nprun argument. And remember, that was the maximum number of terms that can be included into the model. And the fill and the shape aesthetics represent the first parameter that we tuned, which was degree. So here we can see that the optimal model, or in other words, the one with the lowest root mean square error, was achieved right here. So that model corresponded with a value of 4 for the degree argument, and the value 15 for the nprun argument. Now, it's not surprising that the highest degree resulted in the best model, since remember, this is the maximum possible degree. So it doesn't necessarily mean that all of the fourth order interaction terms are included, but it just means that interaction terms that were second degree, third degree, or fourth degree could have been included in that model. Compare this to degree equals 1, where we allow for no interaction terms at all. So when we allow for absolutely no interaction terms, we get a much higher root mean squared error in general. So now if we want to extract that optimal model, so the best one out of the 40 that we trained, that's going to be contained in the object that we created
under the element called final model.
Then we can sort of use that model the same way that we would use any other models in R. So for example, we can use the predict function. So let's say now that we have this trained model, we want to use it to predict the response variable on our reserved test set that we created earlier. So to do that, we can just use the predict function. And the first argument is going to be similar to what we would use anytime that we use the predict function in R, which means that the first argument is the object argument. And that's where we specify what model we want to use. So here, we're saying that we want to use the optimal model, which was this one right here on the plot. The next argument that we specify is the data that we'd like to predict the response for. And that was the reserved test set that we created earlier. If we take a look at Mars_predict, we can see that we've predicted the response variable for each of the observations in the reserved test set. We can see here that we had 102 observations that were predicted, and there were also 102 observations in our reserved test set. Once you have those predictions, you can use any of the performance metrics that you're used to using. So for example, we could compute the SSE. So remember, the SSE is the sum of squared errors. So first we calculate the error, which is the difference between the true value and the predicted value. We square that, and then we sum over the 102 observation. Here we can see we had an SSE of 1495.869. As another example, you could also compute the MAE, which is the mean absolute error, and that is exactly what it sounds like. We take the mean of the absolute differences between the true values and the predicted values. Here, along the y-axis, we have the residuals, and along the x-axis, we have the observation number in the test set. So that's going to range from 1 to 102.